This is Unit 9, Kinetics and Equilibrium, Lesson 3, Potential Energy Diagrams. How are potential energy diagrams interpreted? The objectives of this lesson: I can determine if a reaction is endothermic or exothermic based on the potential energy of the products and reactants. I can label all parts of a potential energy diagram. I can calculate the heat of a reaction, and I can draw a catalyst on a potential energy diagram and describe how it affects the reaction. Do now. Potential energy diagrams show the change in potential or stored energy during a chemical reaction. This is an example of a potential energy diagram. On the left, we have the potential energy of the reactants, and as the reaction progresses through time, we see that potential energy change, and on the right, we see the potential energy of the products. So there are two types of potential energy diagrams. Endothermic potential energy diagrams show a product side that's higher than the reactant side. And why is this? This is because energy is absorbed by the reactants, so the net amount of potential energy increases. That is why we get a positive delta H. So looking at this potential energy diagram, we see here's the energy of our reactants. As the reaction progresses, we see an increase up to the very peak, and then we have a decrease come back down to the potential energy of the products. And notice that the product side is higher than the reactants, so we have a positive net change. This is where that energy was absorbed. Excuse me. Exothermic potential energy diagrams show the product side lower than the reactant side. And why is this? This is because energy is released as a product, so the net amount of potential energy decreases. That is why we have a negative delta H. And looking at this example of a potential energy diagram, we see the reactant side energy here. As the reaction progresses, we go up to the very peak and then back down to the potential energy of the products. And notice the products are lower than the reactants with a negative net, and this is where our energy was released. Stop and think. Parts of the potential energy diagram. This is one of our key concepts for this whole course. This is one of the important diagrams that we expect you to understand. So you must be able to label these. So label the diagrams in your notes as we go through this. The activation energy is defined as the minimum energy required for a reaction to occur. This is the energy needed to get over the hill. So if we look at our two different types of potential energy diagrams, the activation energy always starts as at the reactants, and it goes all the way up to the very top. So from this dotted line on the reactants energy up to the dotted line at the very peak. For an endothermic reaction, that energy is always going to be higher, or it's usually going to be higher. In the reactant side, we can see that it's also from the reactants energy up to the peak. That's our activation energy. And if we look at this little analogy here, this little guy has to push the rock up over the hill. That's the activation energy before he can just roll it down the other side. Here's a very short video that shows this with a chemical example.
If oxygen and methane molecules are mixed together in the same container, they collide. But there is no reaction until a spark or flame is added. Why? To react, the molecules must collide with sufficient energy to break the oxygen-oxygen bonds and carbon-hydrogen bonds so new bonds can form. The additional energy needed to break existing bonds and start the reaction is called activation energy. An energy diagram can help show these energy changes. Initially, the oxygen and methane molecules collide, but do not have sufficient energy to react. A flame can supply the activation energy needed to start the reaction. At this point, bonds break and new bonds form in an exothermic reaction that releases energy. The energy released supplies the activation energy for other molecules to react, and the mixture explodes. In the air, nitrogen and oxygen are continually colliding, but lack sufficient energy to react. Heat from lightning supplies the activation energy to break bonds, and new bonds form in an endothermic reaction that absorbs energy.
The activated complex is defined as the highest energy point of the reaction. It's temporary, and this is where the bonds are broken and reformed. So the activated complex is going to be up here at the top. I'm going to label A sub C, A sub C. That's your activated complex at that very, very peak. The heat of the reactants and the heat of the products are the amount of potential energy possessed by the reactants and product. So that's going to be our delta H down here for our reactants. Oh, that's a delta. That should be a delta. Let me make this clear. Why I did that, I don't know. Delta H for our reactants, delta H for our products. Actually, it's not delta, it's just H. H of the reactants, H of the products. So for the reactants, it's always on that left-hand side. And for the products, it's always on that right-hand side. So stop and think, what are these four areas on this energy diagram? Oh, actually, I should, anyway, we're going to just say that didn't happen. The delta H, the heat of the reaction, is the amount of the energy lost or gained in a reaction. So you're going to always subtract the products minus the reactants. So to calculate the delta H, it's the energy of the products minus the energy of the reactants. I'm going to make this more clear. The energy of the reactants is that distance from the bottom up to the top, and the energy of the products is that energy from the distance from the bottom to the top. So stop and think, what is the delta H of this reaction? And stop and think, is the delta H positive or negative for this reaction? The effects of adding a catalyst, they lower the activation energy. That's why it can go faster. That activation energy is the energy needed to start the reaction, and therefore the reaction occurs faster. When we draw it on a potential energy diagram, what we'll do is draw an activation energy where the reactants start at the same place and the products end. However, this distance from the bottom of the reactants to the top is lowered. That's that activation energy, and that's how you would draw a catalyst, the effect of a catalyst on a potential energy diagram. The way it works is it allows the reaction to occur by an alternate pathway. So if we use this little guy as an analogy, with the wheelbarrow, he's got to go up and over the hill. But with the catalyst, he can just sort of go through the hill or next to it on a lower side. So it's an alternate pathway. He went somewhere different, and he lowered the activation energy and made the reaction go faster. So check your understanding. I basically just told you that answer. All right, now you can determine if a reaction is endothermic or exothermic based on the potential energy of the products and reactants. You can label all parts of a potential energy diagram. You can calculate the heat of a reaction, and you can draw a catalyst on a potential energy diagram and how it affects the reaction.